Hey everybody, Mr. G here. Welcome back. What we're going to be doing today is we're going to be doing the next in the lecture series for Power Electronics ELIC 316. And what we're going to be focusing on today is lab number 4, which is the SCR and the triac as an AC switch. So if you remember from the last lecture, we have different thyristors, and the two that we're going to be focusing on this week, SCR and the triac. So the SCR is a one-directional device, and the triac is a bi-directional device. With the SCR, remember it has to be forward biased, so that means the anode must be positive with respect to the cathode. And then we need a positive gate trigger voltage, and it's going to be greater than what's in the specs. Once we have those two conditions, then the device is turned on. It will remain on as long as there's current flowing through the device, and that current is greater than the holding current, which you will also find in the specs. At any time when the current through the device drops below the holding, the device turns off. For a triac, it's a bidirectional device, so you can have forward reverse bias. The gate trigger voltage is also bidirectional. So once you have a bias and a gate trigger voltage greater than the spec, the device will turn on. It will remain on as long as there's current flowing through the device and that current is greater than the I holding. Once the current falls below I holding, the device turns off. So what we're going to do is we're going to look at how that now works in an AC system. So an SCR in an AC system, so this is the circuit from the lab. So we've got the SCR, we've got an AC supply, a couple of switches just to control our current flow, a resistor to limit the current into the gate of the SCR. So very similar to what we did in lab number 3, only difference is instead of having a DC supply, we're now going to have an AC supply. And what it looks like is, there's our AC supply. So, our AC supply is connected here in the circuit. It supplies electricity both to the load and to the gate trigger circuit. So the idea is if I was to close both of these switches, whenever we had enough voltage at the gate to turn the device on, it will conduct, the light bulb will light. It will remain conducting as long as I have current flowing through the device. If somehow the current falls below the holding value, then the device turns off and the light bulb turns off. So what we're going to do is we're going to pretend that we are hooking up a scope from the anode to cathode in that circuit. In the lab, we also hook up another scope on the gate circuit from gate to cathode. So here we're looking at the voltage gate to cathode, And here we're looking at the voltage anode to cathode. So what happens in this circuit is if we were to close these switches and apply this AC waveform, right here at 0 volts, this device will not be turned on for 2 reasons. 1, there's no bias voltage yet. 2, there's no gate voltage yet. So as this starts to climb, so as the voltage applied starts to climb, eventually it's going to reach a point where we have enough voltage across the anode cathode and we have enough voltage across gate to cathode. At that moment in time, and we will call this the gate trigger voltage. At that time, we have the conditions required to turn this thyristor on. So, if we were to look at the voltage from anode to cathode, I'm going to mark it in red. So from the 0 point, the device is off, so the voltage is allowed to climb. Once we hit a point where the voltage is great enough to turn on this device, the voltage across the device, because remember the voltage across a closed switch is 0, so that voltage drops. That voltage will remain. And this time here, the device is turned on and our light bulb is lit. Eventually what's going to happen is as the voltage applied is going through the SCR, it's going to die off, and it's going to reach a point where the current that this voltage will produce is below our holding current. So let's say right there. So this would be the point where we fall below the holding current and the device turns off. So typically what we have is we have a spike on this side as the voltage has to increase to a point where it's large enough to turn on the device. The device is on during this time until the voltage falls and gets close to the 0 reference. Eventually, somewhere around here, what's going to happen is the voltage is going to fall to a point where it can no longer maintain the holding current and the device shuts down. So this is the time when the device is on. That time is known as the conduction angle. So the conduction angle is defined as the amount of degrees out of our 360 degrees. So we have 360 degrees in one waveform. So out of that 360 degrees, how long is the device on? That's our conduction angle. So in order to figure all that out, we have to figure out what's going on the other half of our waveform. Well, since we know from previous lecture that the SCR is a unidirectional device, so that means that the device remains off for the entire time that the voltage is negative. So, once this whole thing starts up again and the value grows, it reaches the trigger value, turns on, and the whole thing repeats itself. So, once again, from 0, the voltage has to grow large enough to actually reach the trigger voltage. Once that happens, it turns the device on. So the voltage across a device is approximately 0. It's not exactly 0 because it's not a true switch. It's a semiconductor switch. So the voltage across the device is close to 0. It will remain on until such a time as the voltage that's flowing approaches 0, therefore causing the holding current to approach 0. So the current through the device is going to approach 0. It falls below that spec, that minimum spec for holding, and the current is shut down. So the device is turned off. The result is a conduction angle. So the conduction angle is a measurement in degrees of how long a device is conducting in our 360 degree waveform. So in this case, with an SCR, you can see the conduction angle is going to be less than 180 degrees. So we lose this little time, we lose this little time, and the conduction angle is somewhere less than 180 degrees. Once the waveform starts to grow again and repeat itself, the same thing happens. So again, we're left with two little spikes. One spike is when the device reaches the voltage that it's able to turn itself on. The second spike is the point at which the current in the device falls below the holding spec and the device turns off. So that is the SCR in the AC environment. Now let's take a look at the triac in the AC environment. Again, what we would do is we're going to monitor with a scope from main terminal 2 to main terminal 1, and same thing here on the gate. So what we're going to do is we're going to look at it exactly the same way as we did the SCR. So, starting at the 0 point on our waveform, we're going to close both of these switches. As the voltage starts to rise, eventually it's going to reach the point where we achieve the trigger voltage. At that point in time, our triac will turn on and conduct. As the voltage dies off and approaches zero, again, somewhere along that line, we're going to hit the point at which we can no longer maintain the current flow through the device that's larger than our holding. So the device will shut down. So this is for the eye holding again. Now, here's where the difference happens. A triac device is bidirectional conduction and bidirectional gate. So we figured that out from lab number 3. So as the voltage starts to climb in the negative direction, we will hit the gate trigger voltage on the negative side. The triac will start to conduct, and it will remain conducting until such a time as the current through the device falls below the holding. And then the whole cycle starts over again. So now the device is on here and on here. So if we looked at the conduction angle again is the amount of time in degrees that the thyristor is turned on within one period. So if we look for the SCR, it's only turned on for something less than 180 degrees. For the triac, it's double this. So we're on for that same time pretty much, and then doubling it. So here, the conduction angle will slightly be less than 360 degrees. So here it's slightly less than 180. Here it's going to be slightly less than 360 degrees. So because the triac is a bidirectional device, it also conducts during the negative side of our waveform, therefore doubling our conduction angle. So when you take your measurements in lab number 4, the waveform that you should get when measuring the voltage across the thyristor, in the SCR, your waveform should look something like this. When doing the triac, your waveform should look something like this. So again, focusing on the red waveforms here. So the light blue waveform is the voltage that's applied from the source. The red is the voltage that is across the thyristor. So the thyristor, if the thyristor is matching the blue waveform, the thyristor is off. If the thyristor is a straight line close to the zero, the thyristor is on during that time. So these are the waveforms that you should be getting for lab number 4. So a couple of little comparisons. The SCR in AC versus the triac in AC. So the SCR is going to have a conduction angle which is going to be less than 180 degrees. In a triac, the conduction angle will be slightly less than 360 degrees. In the SCR, we only conduct in the positive side of the waveform. Here, we are having conduction in both sides. So lab number 3 was the same thyristors in DC. Lab number 4 in AC. What's the difference? Well, the big difference is when a thyristor in DC, once you turn it on, it will remain on. Until such a time as you stop the current from flowing. So you've got that holding current issue. So you have to stop that from flowing. So you have to open up the switch or whatever. A thyristor in AC, once it's on, it will shut off automatically every time the waveform approaches 0. So when the input is close to 0. So what does that mean? Well, let's take a look. Alright, so let's take a look at these side by side. The triac in DC versus the triac in AC. So, when I close both of these switches, the light bulb will come on because the thyristor will conduct. If I open up this and remove the gate voltage, the light bulb will remain on because the thyristor remains conducting. And this will stay until I open up that switch and stop the current. So once again, I close the 2 switches, the light bulb comes on. I open up the gate switch, the light bulb remains on. In the AC version, I close both the switches, the light bulb comes on because we're conducting. As soon as I open up this and stop the gate, the next time the waveform crosses the 0 point, the light bulb will turn off because the device stops conducting. If I close the gate switch again, we will start conducting and the light bulb will come on. When I open up this switch, when the waveform naturally crosses 0 the next time, the device will shut down and the light bulb turn off. So here, I open the gate, the light bulb remains. Here I open the gate, the light bulb will shut down as the waveform crosses 0 the next time. And that's the difference between a thyristor in the DC world and a thyristor in the AC world. So I hope this helps. Until next time, everybody stay safe. Take care.